Hello, welcome to Soft Papers channel. I am Godfrey. In this video, I'm solving a Cambridge A2 physics topic. The topic is ideal gases. These are the questions that were set about ideal gases on November 2019 exam series for A2 physics. I always encourage my students to consider revision, doing their revision topic-wise. Read a given topic and attempt the questions for that particular topic in the several years that you can allocate 2019 going backwards, when the content of that topic is fresh in your mind. This way you'll get the most out of the topic. You'll know the key areas to focus on. You'll know the areas that examiners are fond of testing, and you'll be all set. And this is a sure way of getting your A star if you do all the topics topic-wise. Then after you're done the topics topic-wise, the revision topic-wise, then you can come back now to attempt full past papers, and then this way you'll find it easy. Physics is easy only when you do it the right way. So before we start, if you have not already subscribed to my channel, please click the subscribe button and hit the bell icon below. This way you'll be notified every time I upload a new video. Let's get started. These questions on ideal gases was set on paper 4.1, and this was question number 2 of November 2019. 702. This is the code for physics exam, A-level CIE. So you can always use this to refer and refer to the past paper of the marking scheme. If you so wish, marking scheme, I encourage my students. They are meant for teachers or for the examiners, for the markers. Consult your teacher for every given question. This way you'll get the most help as you prepare for your exams. Number 1M. The kinetic theory of gases is based on a number of assumptions about the molecules of gas. Kinetic theory of gases. Of course, state the assumption that is related to the volume of the molecule of the gas. There are a few assumptions on ideal gas, and here we need to state the assumption that is related to volume. And the assumption that is related to volume is that total volume of molecules is negligible. That is, that molecules in an ideal gas does not occupy a volume, and this is when you compare to the volume of the container. So if you consider all the total volume, or if you consider the volume of all the molecules present in that container, so the total volume of the molecules is negligible. It is of no significance when you compare it to the volume of the container, where the molecules are held. When you compare to the volume of the container, compared to the volume of the container. So that is the assumption that we make. Of course, the other assumptions, like the collisions between the molecules and the side of the container is elastic, and so on and so forth. The volume do not exert any attractive force between themselves. So those are some of the assumptions that make that we based on kinetic theory of gases, which help us on ideal gases. Part B. An ideal gas occupies a volume of this meters cubed at a pressure of 4.60 times 10 raised to power 5 pascals, and at the temperature is 23 degrees. Calculate the number of molecules in the gas. Of course, to calculate the number of molecules in the gas, this is the equation we use. PV is equals to nRT. There is pressure times volume is equals to number of moles times the gas constant times temperature in Kelvin. Of course, the temperature is given as 23. You change it to Kelvin by adding to 273 plus 23. This will give us 296 Kelvin. And R is equals to 8.31. You'll get this one from your data. That is given in page 2 or page 3 of your exam paper. So the pressure given here is this, and the volume is given is there. So you take that down. So 4.6 times 10 raised to power 5 times 2.4 times 10 raised to power minus 2. It is in meters. If it was in centimeters, you need to convert it to meters. And therefore, this is going to be equal to N, because you need the number of molecules. You need the moles, and then you convert that into a number of molecules, times 8.31 times 296. So we need N. So N is 4.6 times 10 raised to power 5 times 2.4 times 10 raised to power minus 2. All of these divide by 8.31 times 296. When you do that, you're going to get 4.49 moles. Right, we have the number of moles there. We know that the number of moles is equals to moles is equals to number of molecules divided by the Avogadro's constant, which is 6.02 times 10 raised to power 23. So we need this. So therefore, the number of molecules is equals to N times Na. Therefore, N is equals to number of molecules, which is 4.49. Avogadro's constant is 6.02 times 10 raised to power 23. When you do good calculation, get 2.7 times 10 raised to power 24. Of course, the number is 2.7 times 10 raised to power 24. Don't forget, 1 mole has got 6.02 times 10 raised to power 23 particles. Particles could be atoms, molecules, etc., even people, as long as they are particles. That could be particles. Part 2. Each molecule has a diameter of 3 times 10 raised to power minus 10 meters. Estimate the total volume of the gas molecules. Estimate the total volume of the gas molecules. Of course, the gas molecules is what we have calculated up there, 2.7 times 10 raised to power 24. So we say that volume of molecules, of course, molecules, we take them to be spherical. So we take the formula of a sphere, which is 4/3 pi r cubed, and therefore it's 4 times 3 times pi times radius. We're given the diameter, so we take half of that, 3.0 times 10 raised to power minus 10 divided by 2. Then we cube this. When you do that, you're going to get 1.41 times 10 to the power of minus 29 meters cubed. So our volume of all the molecules, one molecule is this volume, so volume of all molecules is going to be equal to 2.7 times 10 raised to power 24 times the volume of one molecule, which is 1.41 times 10 raised to power minus 29. Of course, when you do correctly, you get the the answer is 4.0 times 10 raised to power minus 5 meters cubed. So 4.0 times 10 raised to power 5 minus 5, sorry, meters cubed. Very well. Part C. By reference to your answer in B part 2, this one here, suggest why the assumption in A is justified. Of course, you can notice that this volume, 4.0 times 10 raised to power minus 3, is much less than the volume of the container, which we had gotten up, which we are given here. The volume of the container, which is here. An ideal gas occupies a volume of this, right? So when you consider the volume here, then the volume is much smaller. When you consider this volume, is much smaller. So you say 4.0 times 10 raised to power minus 5 meters cubed. That volume of all the molecules combined is much less. Is much less than the volume that is occupied by the gas, which is 2.0 times 10 raised to power minus 2 meters cubed. So the volume of molecules is negligible. Volume of molecules is of no significance. Significance is negligible. Of course, you can also try this by getting 2.4 times 10 raised to power minus 2 divided by 4.0 times 10 raised to power minus 5. Of course, this is going to be 6. So this is going to be 6 times 10 raised to power 3. This is 6,000. So the total volume of the container is 6,000 times the total volume of all the molecules. Therefore, of course, this volume, or the total volume of all the molecules, is negligible. You can see the ratio is just too large. It's negligible. Good. You may get these questions I'm solving right here from solvedpapers.co.uk side. The side I'm talking about is right here. This is solvedpapers.co.uk. Of course, it's a very resourceful site rich in CI materials, and you need to come to physics A level 2019. It is, of course, you can get papers for the other years. 2019 A2 right there. Of course, click there and then you'll come right here. This is 2019 physics A2 topicals for both November and June. What you are dealing right now is ideal gas for November. Need you to come and get it from here. Of course, you can get all the topicals for June and November by clicking this green button here. You'll come to this site here, this page. Of course, this page has got both physics, chemistry, and mathematics for A2. Of course, I need you to request your parents to get you these papers. They're only going for £10, and you can get for November and also for June right here, and also for these other years. Get as many as you can, and practice. You be sure to get your A star, and I'm sure you'll be happy with that. I also do online tuitions. If you need my help, you can get me at spacademy.co.uk. I might show you that. This is the site I'm talking about, SP Academy for Software Papers Academy. Of course, here we are doing ICT, mathematics, physics, biology, and chemistry. If you need my help, you can have time and go through our site and get familiar with it. Of course, I need you to check the student guide here. Click here to get the student guide, and also watch this video to be familiar with the online live classes. Once you make up your mind, you need an assistant to the comfort of your house. I need you to click here to register if you have not already done so. I need you to register to create your own account. Provide the correct email address. We will send you an activation code which you need to activate your account, and then of course you can come in here and sign in and access your account. From your account, you can click Find Tutor, and you can choose with several tutors on board. My name is Godfrey. You can talk to me. I'll be able to help you. Of course, if you're only one student, if you want a one-on-one with me, this will be basically £35 per hour. If you bring with you 3 students, so that you have 4 students, I'll give you a discounted price of £25 per hour. So come on board, let's learn physics together, and let's help you get your A star. I've helped many students, and I'll be glad to help if you need my help as well. Well, that's out of the way. Let's continue with question number 2. Question number 2 was from variant 4.2, and this was number 2 of October-November 2019. So, smoke particles are suspended in still air. Air is not moving. Brownian motion of the smoke particle is seen through a microscope. Describe what is seen through the microscope. Of course, when you have some smoke particles in a smoke cell, and you place them under the microscope and you illuminate the smoke cell with light, then you'll see specks. You'll see specks of light. Of course, this light is the light that is reflected by the molecules of the smoke. Not molecules, the smoke particles. Smoke particles are big enough to be visible under microscope. Moving in a haphazard motion. So moving haphazardly. So specks of light. So you'll be see dashy light moving haphazardly. Those are the smoke particles. Describe how Brownian motion provides evidence for the nature of movement of gas molecules. Right, you say what you'll be seeing is a haphazard motion, what we call random motion. So the haphazard motion is due to the haphazard motion. The haphazard motion is due to the smoke cell. So the haphazard motion of the smoke cell, so not the smoke cell, the smoke particles, is caused, because we cannot see the air molecules. The air molecules are the one that are knocking the smoke particles. Is caused by the collision. Of the smoke cells with air particles. The smoke cells or the smoke particles with the air molecules, or what we can call the gas molecules. So when the gas molecules that are moving in haphazard motion collide with the smoke particles, then the smoke particles which are visible to us through the microscope will appear as moving haphazardly, will appear as specks of light when the light is reflected on the smoke particles, moving haphazardly. So it is the gas molecules that are moving, and therefore when they collide with the particles of the smoke will move haphazardly, and therefore Brownian motion provides the evidence for the movement of gas molecules in that context. Part B. A fixed mass of an ideal gas, has a volume of this, and at a pressure of this. The temperature is 290 Kelvin. The gas is heated at constant volume. The volume is not increasing, and the temperature has risen to 310 Kelvin. Of course, you can see the pressure has increased from 3.5 times 10 raised to power 5 to 3.75 times 10 raised to power 5. As illustrated, the temperature has increased, pressure has increased, but volume has stayed constant right there. The quantity of thermal energy required to raise the temperature of 1 mole of the gas by 1 Kelvin at a constant volume is this, 12.5 joules. Calculate to 3 SF. The amount in moles of the gas. We need to know how much gas do we have here, since we are told to raise the temperature of 1 mole by 1 Kelvin, we need an energy of 12.5 joules. Now we can see here the temperature is given right there. So what we need to find is the number of moles here. So the equation to use is pressure times volume is equals to the number of moles times gas constant times temperature in Kelvin. So N will be PV upon RT, and of course PV is the pressure, which is given right here, 3.51 times 10 raised to power 5 times the volume, which is given right here, 2.4 times 2.4 times 10 raised to power 3. Gas constant is 8.31. This is given in your data booklet, times the temperature, which is 290. So you put all these in your calculator and do the correct evaluation. You get the number of moles is 0.35. So 0.350 is the number of moles. Calculate to 3 SF the thermal energy transferred during the change. Of course, we are told up there, we are told that 1 mole, we are told the thermal energy, 1 mole at a temperature of 1 Kelvin transfers 12.5 joules of energy. Now, here we're given, we have calculated the number of moles to be 0.350 moles. Okay, the temperature was from 290 to 310. Then at that temperature, what is the amount of energy that is going to be transferred? Therefore, you just cross multiply straight. So you'll get 0.350 times this temperature change, which is 310 minus 290, of course, times 12.5 joules, and this is divide by 1 mole times 1 Kelvin. Of course, this Kelvin, this is mole. The moles will cancel. So when you do this and do correct calculation, then you'll get an energy that has been transferred is 87.3 to 3 SF. So 87.3 joules right there. For the change in the gas in B state, the quantity of external work done on the gas, right? Since the volume of the gas stays the same, you can see right here the volume of the gas stays the same, 240. So it did not expand, and therefore if it did not expand, then there was no work done by the gas to the environment. So the work done is equals, of course, to force times change in volume, and since change in volume here is 0, then work done, which is force times change in volume, will be equal to 0. So we have said that the gas did not expand, the volume stays the same, did not expand. So we know that V1 is equals to V2, and work done is equals to force times change in volume, right? But change in volume here is 0. So work done is equals to force times 0, which is equals to 0. So work done is 0. For the change in the gas in B state, the change in internal energy with the direction of this change. Of course, the change in internal energy is equivalent to this, which is 87.3 joules, and the direction is it will increase. The internal energy will increase. The molecules, or the gas molecules, will be more energized, and of course the temperature will increase, and also the kinetic energy will go up. Good. These are the only two questions that were set in the topic of ideal gas in October-November series. Look out for more topical questions in solvedpapers.co.uk, and do as much practice as you can. Hopefully I'll see you in my next video. Cheers.